Don't know what happened to my one note, so it is back to me. Okay, so what we're looking at here is a single slit example. And let's just quickly draw the single slit so we kind of have an idea of what's going on. Here is a single slit. Here's some viewing screen back here, which I won't bother to draw. But we know we're going to get kind of like a central peak, and then, it's going to keep doing its thing. That's really bad over there at the edge. What is going on there? A bright point, dark point, bright point. You get the idea, okay? Where this is dark and dark. This takes place at a wavelength and a negative wavelength away. So what we're trying to do in this problem is we are trying to look and find what is the angular width of the central peak. And an angular width is actually an angle theta. And then we're trying to find out what is the linear width, like in centimeters or meters, okay? So just some actual like length of this central peak. And we're going to do this for monochromatic light of a wavelength of 750 nanometers. And 750 nanometers is definitely a red light. Around 700 nanometers is red light. Around 400 nanometers is a nice violet. And we know that our single slit width here is 1.0 times 10 to the minus 3 millimeters. And I don't know why that 10 is up there. It should be down there, but whatever. Okay. And our viewing screen, so maybe I should draw the viewing screen, whooshing, poorly drawn, is 20 centimeters away. So let's try to solve this out. If we think about our double slit equation, we know we have two of them. We've got d sine theta equals m lambda, and d sine theta equals the quantity m plus 1/2 times lambda. And if we're trying to figure out information about the central peak, what we really need to think about is the fact that our central peak is bounded by these dark points, okay? The central peak is bounded by the darkness. So if I can use this dark point, and if I can find the angle of the dark point then that will allow me to say, look, our central peak is within those two dark regions within that angle. So I actually want to use d, and we're using a capital D here for a single slit. I actually want to use d sine theta equals m lambda for our dark points, because these dark points bound our central maxima here, okay? They bound that central peak, okay? And remember, that central peak is actually including the lambda over 2 and negative lambda over 2, which is a little different from our double slit. So if we go ahead and do this, since this is our first dark point here, it's our first dark fringe, we know that m is just going to simply equal 1. Remember, these m's are just integer values. We saw that with our double slit, with our double slit. And we know a value of lambda here. We're given it. And we know what d is. D is this slit width here. So if we want to find theta, we can actually do that. We can say here that theta equals m lambda over d, and then we just take the arc sine of each side. This is very similar to something that we did with the double slit and looking at angles for that. And in this case, we'll just have the inverse sine or the arc sine of 1 times 750 nanometers. So let's just write 750 times 10 to the minus 9 divided by, what is this? This is 1.3 times 10 to the minus 3 millimeters. I'm being such a jerk. So that's like 1 times 10 to the minus 6 meters. And if we kind of start chunking through numbers, we'll find that theta is the inverse sine of, oh boy, let's calculadoro this. Let's see, 750 times 10 to the minus 9 divided by 1 times 10 to the minus 6. Let's see, that's 0.75 naturally, but then we need to take the inverse sine of 0.75, which I don't know off the top of my head. But it is, oh, what do we get here? 48.6 degrees. So this is going to be 0.75, and the inverse sine of that is 48.6 degrees. So that is what this angle is up here. Now, that is not the entire angular width of our setup. Our entire angular width is from the top line to the bottom line. So I want this whole thing. But luckily for us, there is symmetry here. So if I found the top angle, that angle is equal to the bottom angle. So I can just say twice or 2 times 48.6 degrees gives me the entire angular opening of our central peak. So we'll just multiply that by 2, and we get something around 98. It's actually about 97.18 degrees. So that is the angular size of our central peak. And if you're like, wait a second, is that allowed to be greater than 90 degrees? Sure it is. Think of it this way. If you have an eyeball here, if you could magically see with your perfect peripherals up, or like perfectly left and perfectly right, that's 180. What we're saying here is that we are just encompassing something a little bit more than 90 degrees. So maybe that's like a little bit more than 90 there. That's totally fine. That could be 97 degrees there. Okay, so that's all we're saying here. This is the angular opening of our central peak. Now, to actually find the linear size of our central peak, we need to do a little bit of SOHCAHTOA. And the reason being is when we're talking about a linear size, what we're really talking about is we're saying, what is this actual length dimension on the backside here? And what we'll do to find that is we'll set up a triangle going across, up, and then back on this diagonal path. And this triangle is very easy for us to solve because we were given in this problem that this viewing screen is 20 centimeters away, and we happen to have just solved this angle here is 48.6 degrees. So it's a little bit of SOHCAHTOA. We could easily solve for this side right here. If we actually do SOHCAHTOA this, we notice that this is the opposite side and this is our adjacent side. So we're going to be using a tangent here. And what we find is that the tangent of our angle, 48.6 degrees, is equal to the opposite side, which is actually what we're looking for. We're looking for, some dimension over here. We'll just call it x, divided by 20. That's in centimeters. And we multiply 20 centimeters on each side. We do 20 times the tangent of 48.6. And we find that x here will equal 22.68. And the units are centimeters because that's what the first value was. And then if we know that just this upper triangle is 22.68, we know the bottom triangle down here has to be the same amount. So we can just double this. And we'll find that the full value of L that we're looking for is just, what is that? 45 point something something. 45.37 centimeters. And this is the linear width of our central peak. So that's how we can go ahead and define what our central peak is. We do it by looking at the dark fringes, because these dark fringes, they border or they box our central peak right here. We know we're going from dark to dark, and everything in between that is a bright, or is that central fringe. And by using the single slit equation for a dark, which is just m lambda, we can quickly work out, just like we did previous problems, to figure out what both an angular size is, the 97.18, and the linear size is dimensionally on the screen. If we brought this viewing screen in closer to that slit opening, our angular size would be the exact same, but our linear size would be different. We haven't given then this viewing screen enough time, or enough distance rather, to spread out. So what would occur here is this denominator of 20, if that was only like 1 centimeter, when we bring it over and multiply, we quickly see that this x value changes. So, another way of kind of showing that is just imagine for a second if your viewing screen was only right here versus if your viewing screen is back here, right? It's the same angle we're looking at, 97 degrees, but this is a much larger value than this right here. So that's the only thing that would change as you move closer or further away. The linear, like true distance of the central width will change, but the angle will stay the same there. Just a property of some basic geometry. Okay? But with that, this problem is finished. There's not much more left in the world of wave optics. The single and double slit have been solved for us. We've completed those. We just have thin films left, and we'll see that in some later videos. But until then, adios. Take it easy.